Imagine a world where energy is limitless, clean, and safe. No smoke from coal plants, no radioactive waste piling up, no dependence on oil or gas. Instead, a power source that mimics the sun itself, fusion. For decades, scientists have promised us that fusion is the ultimate solution to humanity's energy problems. And for just as long, critics have joked that it's always 30 years away. But today, we're closer than ever before. Around the world, experimental fusion reactors are finally pushing the limits, and some are nearing what's called net energy gain. That's the holy grail of fusion, producing more power than they consume. So, let's break it down. What exactly is happening right now in fusion research? How close are we to powering our cities with star-like energy? And what are the biggest challenges still ahead? Fusion is not just another energy source. It's the very process that powers our sun. At its core, fusion means taking lightweight atoms, usually isotopes of hydrogen like deuterium and tritium, and smashing them together under extreme heat and pressure. When they fuse, they release enormous amounts of energy, far more than chemical reactions like burning fuel. The best part? Fusion doesn't produce greenhouse gases. It doesn't leave behind long-lived nuclear waste. And the fuel, hydrogen isotopes, can be extracted from water and lithium, resources found across the Earth. That's why fusion has been called the energy of the future, the energy that could power civilization for millennia. The only problem, it's incredibly difficult to achieve. To replicate the sun on Earth, you need temperatures of over 100 million degrees Celsius, powerful magnetic fields, and flawless engineering. For decades, that challenge has kept fusion as a dream rather than a reality. But something exciting has changed in just the past few years. We are finally hitting milestones that scientists only dreamed about before. In 2022, researchers at the National Ignition Facility in California achieved a world first. Using powerful lasers, they managed to create a fusion reaction that released more energy than the lasers delivered into the fuel. This was the first time in history that fusion crossed the threshold of net gain, even if only for a split second. Meanwhile, in Europe, the jet reactor in the UK set records for the most sustained energy output from fusion ever achieved, holding plasma for 5 seconds and producing 59 megajoules of energy. It wasn't net gain yet, but it showed that reactors can handle the extreme conditions fusion requires. And then there's ITER in France, the massive international project that has been under construction for decades. ITER isn't online yet, but once operational, it aims to demonstrate large-scale fusion with a 10-fold energy gain. In other words, for every unit of energy put in, it could release 10 back. These aren't just small experiments. They're proof that fusion is no longer a fantasy. It's becoming a working technology, one step at a time. Now, you might be asking, if fusion is so close, why are there so many different reactors and methods? Well, there's no single path to making it work. The two main approaches are magnetic confinement and inertial confinement. Magnetic confinement is used in tokamaks like ITER and in new designs like compact spherical reactors. Here, powerful magnetic fields shape and contain superhot plasma, preventing it from touching the reactor walls. Inertial confinement, on the other hand, uses intense bursts of energy, usually lasers, to compress tiny fuel pellets until they fuse. That's what the National Ignition Facility uses. And then there's the private sector. Startups like Commonwealth Fusion Systems, Helion Energy, and TAE Technologies are racing to build smaller, faster prototypes. They claim they can achieve net gain sooner, within the 2030s, by using innovative magnets, new fuels, and more compact designs. What's fascinating is that governments and private companies are now working in parallel, like a global competition to see who can light the first practical star on Earth. But let's be clear, there are still huge challenges ahead. Producing net energy gain in an experiment is not the same as running a power plant. Fusion reactions last only seconds or less right now. To power a city, they would need to run continuously, reliably, and at industrial scale. Then there's the engineering challenge. The walls of a reactor must withstand neutron bombardment at extreme heat for years without breaking down. The materials for this don't yet exist at large scale. Fuel supply is another hurdle. Tritium, one of the main fuels, is rare and must be bred inside reactors themselves. Developing efficient fuel cycles will be critical for fusion to become practical. And of course, the cost. ITER alone costs tens of billions of dollars. Private companies are promising cheaper solutions, but commercial-scale reactors will require massive investment before they can replace existing power plants. So, the big question, when will fusion finally power our homes? Optimists say within the 2030s, especially if private startups succeed. More cautious scientists say it could be the 2040s or 2050s before we see commercial reactors connected to the grid. But here's the important part. For the first time, this isn't about if, it's about when. The progress made in the last decade has been so significant that fusion feels inevitable. Humanity is finally on the edge of mastering star power. Imagine cities powered by reactors that emit no carbon, produce no long-term waste, and run on fuel from seawater. Imagine a planet where energy scarcity is no longer a threat, where developing countries can leapfrog into clean power without relying on fossil fuels. That's the promise of fusion, not just cleaner energy, but a transformation of our civilization. So, as we wrap up, let's take a moment to think about how monumental this is. For the first time in history, we're seeing fusion reactors come close to producing more power than they consume. We're watching the birth of a technology that could change everything. Our economy, our climate, even our future in space exploration. Yes, the road ahead is long, but for the first time, we can see the light at the end of the tunnel, and that light is literally the power of a star. Now, I want to ask you, do you believe fusion will arrive in our lifetimes? Would you trust your city to be powered by a reactor that recreates the sun on Earth? Let me know in the comments. And don't forget to subscribe for more deep dives into the future of technology, because the next energy revolution might be closer than we think.